Before data can be queried, it exists in a state of pure, multidimensional chaos. Every person, transaction, and location in the real world is tied together by an infinitely complex web of relationships. Relational database management systems cannot process this chaos directly. They require strict, uncompromising order, forcing data into flat, rigid, two-dimensional structures of rows and columns. Architects bridge this gap using the Entity Relationship, or model. This conceptual blueprint maps out the reality of a system before a single table is ever built. The left side captures the organic conceptual web of the model. The right side represents the stark mathematical grid of the final relational schema. Moving from conceptual design to a functional database requires a strict algorithmic mapping process. Every multidimensional concept must be flattened into these tables while perfectly preserving the logical relationships between them. Failing to execute this translation correctly leads to structural anomalies. Orphaned records break free, structural constraints critically fail, and the entire system eventually collapses into an invalid state. The translation process begins by identifying entities. An entity is a real-world object with a distinct existence, like a professor or a student. Entities are categorized by independence. A strong entity, a solid rectangle, has an independent existence. This independence is guaranteed by a primary key. Here, Professor ID uniquely identifies that record across the system, standing alone. However, certain data objects lack this autonomy. Their existence is entirely tied to a parent entity. These are weak entities. In database diagrams, the double rectangle signifies that the object is existence-dependent on another. As the documentation states, a weak entity lacks its own primary key. It cannot be uniquely identified without its parent's context. This diagram shows the connection. The professor is the strong entity. Dependents are the weak entities. To differentiate dependents, the model uses a partial key. The dotted line under name marks it as a local identifier. Distinguishing between these independent and dependent objects is the mandatory first step before any relational database architecture can be drafted. After defining entities, we examine their specific properties, known as attributes. In the model, these are represented by elliptical shapes. Attributes must follow strict structural rules. Simple attributes, like a student's roll number or age, satisfy the rule of atomicity, meaning they are indivisible, single values. Composite attributes present a structural problem. The address node branches into multiple subparts. A relational table cell holds only one atomic value, so architects dismantle these composites. The overarching name attribute is stripped, mapping its components into separate columns. Multi-valued attributes pose a different threat. Represented by double ellipses, these attributes, like a mobile number or email ID, indicate that a single person might possess several values for one property. This creates a structural conflict. A single cell under a phone number column in a table cannot contain an array of 3 different numbers without violating the rule of atomicity. Resolving these attribute violations forces architects to move beyond a single spreadsheet, spawning additional complex table structures to maintain data integrity. We resolve these conflicts through a strict 4-step mathematical algorithm that translates conceptual shapes into a final logical schema. Step 1 maps strong entities. Every strong entity in the conceptual model becomes a foundational table in the relational database. Simple attributes drop directly into the columns, and the unique identifier is permanently locked as the primary key. Step 2 handles weak entities, which require separate tables for atomic organization. We solve their lack of a primary key by importing the parent table's primary key as a foreign key, creating a composite identifier to track the weak entity. Step 3 maps one-to-many relationships. For instance, one department controlling dozens of different employees. To map this relationship, the primary key from the one side, the department, is injected into the many side, the employee table, to establish a logical link. Finally, Step 4 resolves multi-valued attributes. Since one cell cannot hold multiple phone numbers, the model splintering begins. The algorithm spawns a completely new table containing only the individual values, linked back to the parent record via a foreign key. Following these algorithmic steps allows a multidimensional reality to be flattened into 2 dimensions without losing its logical connections. The result of this process is the finalized relational schema, a comprehensive map of the system's logic. These interconnected paths represent absolute mathematical laws designed to protect the data from catastrophic corruption. The first law, entity integrity, dictates that no primary key can ever be blank or null. Every record must be uniquely identifiable. The second law, referential integrity, ensures that every foreign key points to a parent record that actually exists within the system. If a user attempts to delete a department that still has assigned employees, the relational model triggers a constraint violation, blocking deletion automatically. This blockage prevents orphaned records and ensures the database never points to non-existent data, maintaining the logical validity of the entire system. The relational model uses these explicit structural constraints to force a multidimensional reality to remain atomic, interconnected, and perfectly queryable.